Hey guys, welcome to Stat 441 at Virginia Commonwealth University. In this lecture, we will learn about some probability rules that can be used to solve probability problems. First up is the additive rule of probability. And this rule gives us a relation between the probability of union of two events and the intersection of two events. So if we have two events A and B, then the sum of the two probabilities, so probability of A plus probability of B minus the intersection of the two probabilities. So probability of A intersection B, that gives us the probability of A union B, the union of the two events. So if you look at this Venn diagram, we have two events A and then B, and then there is an overlap here of A intersection B. If you think of A union B, then this is the whole surface area that we want to cover. Now, because of this overlap, we have A intersection B counted twice. So we remove that, and that's what we're doing here, probability of A plus B minus the overlapping piece. So that would give us the probability of A union B. So it depends on the problem. If you have information given about any 3 out of 4, you can calculate the fourth probability. Let's look at an example. So here we have a unbalanced die which is tossed and the up race is observed. The two events defined here are A, that you observe an even number, and event B is that you observe a number less than 3. Now, since this is a loaded die, the probabilities will differ from a balanced or a fair die. So here we are given probability of A is 0.4, probability of B is 0.2, A intersection B is 0.1, we need to figure out the probability of A union B. So as you can see here, out of the 4, the 3 are given to us, and we can use the additive rule to find the probability of A intersection A union B. So here is what we are given. Probability of A, which is an even number, it could be a 2, 4, or 6, it's 0.4. Probability of B, a number less than 3, so it could be 1 or 2, and its probability is 0.2. The intersection will have the event of 2 occurring, which is the common element here, and its probability is 0.1. So probability of A union B can be calculated as probability of A plus probability of B minus probability of A intersection B. So that gives us 0.4 plus 0.2 minus 0.1, and the answer is 0.5. If you look at the Venn diagram, this is what is happening. So we have event A here, event B, and then this is the union, or all of this put together, and then we have the intersection piece showing up twice, so we remove it once to get the answer. Here's another example. Records at an industrial plant show that 12% of all injured workers are admitted to a hospital for treatment. So out of all injured workers, 12% are admitted to an hospital for treatment. So probability is 0.12. 16% are back on the job the next day, and 2% are both admitted to the hospital for treatment and back on the job the next day. So let's see what are the three probabilities given here, and then what do we need to find. If a worker is injured, what is the probability that the worker will be either admitted to a hospital for treatment or back on the job the next day, or both? So if you look at this combination, this is union of two events, the probability the worker is either admitted to the hospital for treatment, back on job, or both. So that would be the union of two events here. So let's define our events. A is that the injured worker is admitted to an hospital. B is that the injured worker returns to the job the next day. So these are A and B. We are given probability of A is 0.12, probability of B is 0.16. We are also given that the probability that an injured worker receives treatments and returns to the job next day is 0.02. So that piece is probability of A intersection B. Okay. We need to figure out the probability of A union B, that the worker is either admitted, returns in the job the next day, or both. So it will be probability of A plus probability of B minus probability of A intersection B. So we can calculate that as 0.12 plus 0.16 minus 0.02, which gives us 0.26. So there is a 26% chance that a worker is admitted to the hospital, receives treatment, or both. Okay. Now here's a special case of the events A and B. Two events A and B are mutually exclusive if they do not have any simple events in common. So that is, the intersection is a null set and the probability of A intersection B is 0. Okay, so which we can rewrite our additive rule for mutually exclusive events. This time probability of A union B is simply the sum of the individual probabilities. So probability of A intersection B is 0, so we don't have that. And what remains is A plus B. Let's look at an example. Let's consider an experiment of tossing two balanced coins. Now we need to find the probability of observing at least one head. These are the events defined. A is observe at least one head. That's what we are interested in. B is observe exactly one head. And C is observe exactly two heads. Okay, so in this situation, what we have is we have our event B and C, at least one head and two heads, and the combination of these two will give us the event A. Event A is, let's look back at it, observe at least one head. So exactly one and exactly two, if we combine these two, that gives us the probability of exactly one head. Events B and C here are mutually exclusive, and event A is the probability of B union C. So we can simply add the individual probabilities here to get the probability of A. So these two here are examples of mutually exclusive events. Now that was the additive rule. Let's look at another probability rule, and this is called the multiplicative rule of probability. And this rule is derived from conditional probability that we have seen earlier. So if you recall, the formula to calculate conditional probability is probability of B given A is probability of A intersection B divided by probability of A. Now, if we multiply both sides by probability of A, okay, so we multiply probability of A here and probability of A on this side, then we get rid of this term. And what remains is probability of A intersection B is equal to probability of B given A times probability of A. We can do the same thing with the relation probability of A given B is equal probability of A intersection B divided by probability of B. Okay, again, if we multiply both sides by probability of V, we end up with this relation. A intersection B is probability of A given B times probability of B. So the order is just being switched here. And this gives us another relation, and this is called the multiplicative rule. So if we needed probability of A intersection B, and where A and B are conditional events, so A occurs after B has occurred, then we can use this rule. So let's look at an example here for the multiplicative rule. So here is the example. A state Department of Transportation engineer is responsible for monitoring the sealed bids submitted by construction companies competing to build a new road. Of interest is the event that a construction company called FM Paving will rig the bidding process in order to improve its chances of winning the right to build the road at a non-competitive price. The event is the intersection of the following two events. First is A, that FM Paving bids on the job, and B is that FM Paving rigs on the job. Okay, let's see what else is known to us. Based on the information obtained from the state's computerized bid monitoring system, the engineer estimates that the probability is 0.90 that FM Paving will bid on the job. So probability of A is 0.90. And then the second information is that and the probability is 0.25 that the bid will be rigged given that FM Paving bids on the job. So this time we know that they have already bid. What is the probability that it's rigged? So probability of B given A is 0.25. Okay, we need to find the probability that FM Paving will submit a rigged bid for building the new road. So in this case, we are trying to find the probability of A intersection B. Okay, so here we can use the multiplicative rule of probability. A intersection B is probability of A times probability of B given A. So 0.90 times 0.25, which gives us 0.225. So that's the probability that they will bid and it is rigged. Now here's a special case of using our multiplicative rule or the conditional probability. So two events A and B are independent of each other if the occurrence of B does not change how A will occur. So we know A given B is conditional probability. So A is conditioned on B. What we are saying for independent events is it doesn't matter whether B happened or not. It will not change the probability of A happening. So such events are called independent events. And in this case, probability of A given B is simply equal to the probability of A. So B has no presence here. It doesn't matter whether it has occurred or not. Probability of A still stays the same. Okay. The opposite of A given B is also true. So probability of B given A is equal to probability of B. So events are independent if it will be true both ways. So A given B doesn't matter. It will be just A, and B given A will just be the probability of B. The opposite of independent events are dependent events, where it will change the probability of B whether A has happened or not. Let's look at a simple example and understand the idea of independent events. So let's consider an experiment where we are tossing a fair coin twice and recording the up weights on each toss. So A is the event where the first toss is head, and B is the event that the second toss is also a head. So think about this. We flip the first coin and we get a result, and then we flip the second coin and then we look at the up face. Does it matter what happened on the first coins? It doesn't change anything for the second coin because the second coin is working independently. It has no impact on what happened on the first coin. So these will be the two tossing of the two coins will be independent events. So let's look at the probabilities and try to prove that these two events are independent of each other. Okay, so let's say in this case we have Our sample space, which consists of 4 outcomes, we can observe both heads, we can observe heads and tail head, or both tails. And each event has a simple probability of 1/4. Now let's look at the two events A and B. Probability of B is that the second coin is a head, so it could be HH or TH, which is 1/4 and 1/4, 1/2. Probability of A is that the first coin is a head, so we could have HH or HD, again 1/4 and 1/4, which gives us 1/2. Now let's look at the conditional probability. Probability of B given A is probability of A intersection B divided by probability of A. Now A intersection B is the common element, which is HH. It is in both. And probability of HH is 1/4 divided by the probability of A. So this event is what we are conditioning it on. 1/4 divided by 1/2 is 1/2. So what happened here is probability of B is 1/2. Probability of B given A is still 1/2. It did not matter. It did not change the probability of A. So thus, the two events A and B are independent of each other. So we can always mathematically show two events are independent of each other by proving or by showing that B given A is simply the probability of B, or the opposite, A given A is simply the probability of A. Okay, so in this case, we see that probability of B is 1/2, B given A is 1/2. So this proves that the first toss does not affect the probability of the second toss being ahead. The probability is whether or not we know the result of the first toss. Hence, the two events A and B are independent of each other. Let's look at another example and see if in this case the events are independent of each other. This time we have the experiment of tossing a fair die. We have event A, which is observing an even number, and event B is observing a number less than or equal to 4. We want to prove again if A and B are independent. Okay, so let's see. In this case, A is even number, so it could be 2, 4, or 6, and the probability is 1/2. Probability of B is less than or equal to 4, so 1, 2, 3, or 4, which is 4, 6, or 2/3. A intersection B, the common element between A and B are 2 and 4, so the probability is 2 out of 6, which is 1/3. Okay, now let's assume B has occurred and the conditional probability is A given B. Okay, we could do it either way. It should work either way to prove independent events. Now A given B is probability of A intersection B, which is 1/3, divided by probability of B, which is 2/3. So probability of A given B is 1/2, which is the same as the probability of our original event here. Probability of A is 1/2. So A given B is still the same as probability of A. So these two events here are independent of each other. So we see that the event B occurring does not change the probability of A. So the two events are independent, and we can prove this again by switching the order, and it should give us the same result. B given A is again intersection of A and B divided by probability of A, which is 2/3, which is again simply the probability of B. So therefore, the two events A and B are independent of each other. Let's look at the opposite of independent events. Let's see when the two events are dependent on each other. So here is the example we had seen earlier. The consumer product complaint study, and the percentages of the complaints were based on pre and post guarantee periods and the types of complaint. We have two events defined. A is the cause of complaint is product appearance, and B is that the complaint occurred during guarantee period. And again, we want to prove if A and B are independent events. So if you remember this is the distribution here. We have the three types of complaints: electrical, mechanical, or due to appearance. And then we have during guarantee or after guarantee period. A represents the event that the cause of the complaint is product appearance. So product appearance. And B represents the event that the complaint occurred during guarantee period. So these are during guarantee period. We want to see if they are independent. So again, how can we prove independence? We can prove independence if we can prove the probability of A given B is the same as the probability of A. So we had earlier calculated probability of A given B. Let's look at it again. A given B will be probability of A intersection B, which is 0.32, divided by the probability of B, which is the sum of these three, 0.18 plus 0.13 plus 0.32. So that gives us 0.51. Okay, so A given B is 0.51, and the probability of A is due to appearance, so 0.32 plus 0.03, just 0.35. So in this case, A given B is not the same as the probability of A. They're not equal, and therefore A and B are not independent events, or they are dependent events. So that's all for now. More about independent events in the next video. Thanks for watching.